My name is Nur Shafiqah binti Rasli from the Mechanical Precision Engineering course. Welcome to my presentation to the panel and all the viewers. Under the guidance of Dr. Nur Azmah binti Nordin, I will present about my final year project entitled Synthesized and Characterization of Dual Properties of Nickel-Zinc-Ferrite for Magnetorheological Materials. 5 main outline that will be presented is about the introduction, literature review, research methodology, result and discussion, and lastly about the conclusion and future research recommendation. Smart material whose rheological properties are controlled by the externally applied magnetic field are known as magnetorheological materials (MR), and these properties can change rapidly when there is the presence of the magnetic field. Magnetorheological materials are actively used in engineering application, and it is significantly important as it made the material to be actively respond towards the magnetic field, namely as MR foam, MR fluid, MR grease, MR elastomer, and also MR plastomer. As new technologies have been developed, smart materials have found a large number of applications over the years. For the example, damper in the prosthetic knee joint, brake and clutch, and also vibration absorber. Carbonyl iron powder, CIP, has been widely used in MR materials as it exhibits high magnetic saturation, low remnant, and low coercivity. CIP in MR materials are iron-based, where iron is one of the ferromagnetic material which have strong magnetic properties, and the other example are cobalt and nickel. This CIP is good for MR material because it has high magnetic properties, changeable, reversible, and fast response to the external magnetic field. However, now we are facing problem because of CIP is passive towards electrical field. It has poor electrical conductivity, thus it might limit the use of CIP in advanced MR devices that might need both magnetic and electrical conductivity, such as in smart sensors or robotics. I found out that there is a study about MR prosthetic knee joint where previously the system has applied MR fluid. Modification of the device, however, has changed the material into MR elastomer due to leakage issue. It was found that the magnetic performance towards sensor is brilliant, but electrical performance is passive because CIP is not a dual properties material. Therefore, to overcome the limitation of CIP that is not actively respond towards the electrical field, this project will be introduced for synthesizing new additive known as Nickel-Zinc-Ferrite nanoparticle. The combination of additive and CIP particle are believed can exhibit dual properties of magnetic and electrical conductivity. The term magnetization, or also known as magnet polarization, is defined as the density of magnetic dipole moments when it is placed near a magnet that is induced in a magnetic material. From the magnetic moments, it will produce magnetization that results from the motion of electrons in the atoms or the spin of electrons or the nuclei. When all domains are oriented along with the applied magnetic field, the magnetization could reach the state of saturation magnetization, MS. While the region where the remaining magnetization still left behind in the material when the external magnetic field is being removed is commonly known as retentivity or remnants, MR. And lastly, the term coercivity, HC, or coercive force is referred to the value where reverse magnetic field is needed to bring the magnetization back to zero after being saturated. Here is the brief how nickel-zinc-ferrite powder is being synthesized at the sintering temperature of 1000 degrees Celsius. Raw materials that we need are nickel acetate, zinc acetate, iron acetate, distilled water, and acetic acid as precursor. These constituents from the acetate base are being weighed according to the amount that have been calculated and put into 3 different beakers. 30 ml distilled water is poured gradually into each one of the beaker and then being stirred for 15 minutes using magnetic plate with its magnetic stirrer until a homogeneous liquid is formed. Note that the speed and temperature required are 600 rpm and at room temperature 30 degrees Celsius respectively. These three mixtures are then mixed together and the acetic acid is added while continuously stirring. This is where the mixture is called as sol. The speed remains constant at 600 rpm while the temperature is set to 80 degrees Celsius and the time needed are about 48 hours. The stirring and heating process turns the mixture to the form of dark brownish gel. The gel is continuously heated for another few hours to complete the drying process. Here is the image of dried powder after the process. The calcination process is needed to get a finer residue of nanoscale particle at 400 degrees Celsius for 6 hours. And lastly, the powder is being sintered at 1000 degrees Celsius in the furnace. Here is the image of nickel-zinc-ferrite powder after going through all the process. We are using vibrating sample magnetometer (VSM) for the testing of magnetic properties. The graph presents the hysteresis loop of nickel-zinc-ferrite particle at stirring temperature of 1000 degrees Celsius. From the experiment, the value of magnetic saturation obtained is 59.1 EMU/G. The remanence obtained is 2.30 EMU/G, and the coercivity obtained is 38.97 or state. The magnetic saturation can be achieved when all the domains are oriented with the applied magnetic field. The lower the remanence of nickel-zinc-ferrite particle, the lower the chance to lose their magnetic energy after release of applied field. Nickel-zinc-ferrite particle experience small coercive force as the shape of the hysteresis loop shown in the graph is very small and narrow. Correspondingly, low coercivity in the nickel-zinc-ferrite particle proven that it is a group of soft magnetic material and hence it can be easily magnetized and demagnetized. Low coercivity is important to minimize the hysteresis losses. As the outcome, it is indicated that nickel-zinc-ferrite particle have magnetic properties at the temperature of 1000 degrees Celsius. And for the conductivity test, we are using digital multimeter with 2 probes. However, before begin the testing, nickel-zinc-ferrite powder is compressed to pellet shape as the better way to analyze the electrical properties. From the research, the resistivity is reciprocal of conductivity. High resistivity means that low conductivity because they are inversely proportional to each other. The resistivity of nickel-zinc-ferrite particle is noted to be around 8.1828 times 10 to the power of 9 ohm meter, showing that it exhibits electrical properties at sintering temperature of 1000 degrees Celsius. The synthesization of nickel-zinc-ferrite via sol gel method at 1000 degrees Celsius is achieved. It can be concluded that nickel-zinc-ferrite particle exhibit both magnetic and electrical properties. Perhaps nickel-zinc-ferrite particle would be a great combination with the CIP in MR materials, especially for devices that require response to the applied magnetic and electrical field. As the recommendation for the future research, it will be great if the synthesization of the powder using other ways as polymerization and combustion. In addition, other manipulated variables can be considered during the synthesizing the powder, such as considering pH values and different sintering temperature. It is believed that those parameters could result in impressive transition properties of nickel-zinc-ferrite particle.